the next process I want to talk about is beta decay. Now, beta particles they're just electrons. Okay. The important thing to know about beta decay is that it is associated with the weak interaction. So let me write that down. Involves the weak interaction, and that is why the beta processes I'm going to write out now always involve neutrinos. So in terms of beta decay, there's a couple of sort of subcategories of things that can happen. Let's start with the classic neutron decay, right? So, right, and the way you can think of this is that in the decay process, a neutron becomes a proton. So let me just write that. So neutron becomes a proton, and so plus an electron, and an electron anti-neutrino. So let me just sort of highlight what I'm doing here. So neutrino. A few comments, and in P I think we've talked about the symbols for. So we mentioned neutrinos in the last class. The sort of overbar here just means that it's an anti-neutrino. Anti-particles, right, have the opposite charge as a particle. For a neutrino, which is neutral, that turns out to not come into play. But just one thing I wanted to point out about this process is you can notice that there are some things that are constant. Like we know, you can see, for instance, that electric charge is constant. So we, for instance, started with a neutral neutron, and then we end up with a net charge of 0 on the right side here, right? You have a positively charged proton, but a negatively charged electron, so no change in the net charge. It also turns out that what's called lepton number is conserved. So leptons are electrons and muons and tau particles, and their associated antiparticles and neutrinos. We don't have time to talk about the standard model, unfortunately, but yeah, let's talk about that some other time. Or you can also take a look in Townsend for an intro to that. But so it turns out that you have to keep constant the lepton. So electrons count sort of positive. An antiparticle counts as negative. So you end up with sort of a net 0, having started with no leptons on the left here. To write this to write this particular beta decay out in full with actual nuclei, we can write this generically with the parent. So we have the parent goes to the daughter, okay. And this time, right? So because we are changing a neutron to a proton, we're not changing the total number of nucleons. So the mass number stays the same. However, because we go up in protons, the atomic number goes up by 1. And then we get our electron and our anti-neutrino. A good real-world example of this is the decay of carbon-14. And if you like, archaeology or sort of biology, you might be aware that you can use sort of the abundances of carbon-14 versus carbon-12 to date like ancient artifacts or things like dinosaur bones, and we can do that because there's this that carbon-14 undergoes this decay process to nitrogen 7 plus an electron plus our neutrino. So also just we can once again use conservation of energy to set a limit on what is possible, right? So this decay requires the following statement to hold true about the atomic masses. It requires the atomic mass of the parent to be greater than or equal to the atomic mass of the daughter. This requires a word of explanation, right? So the in this kind of decay process, the electron just arises. It is not, right? It is not one of the electrons that's already in the parent atom, right? So like carbon having 6 protons also has 6 electrons. This electron is not one of those 6. So when we actually look at when we want to actually compare the masses of the nuclei, right? So it turns out, right, the atomic mass of a nitrogen atom actually includes the extra electron, so the 7th electron that sort of normal unionized nitrogen has. So if we take this atomic mass, that actually includes the mass of the beta particle that's emitted in the decay. And that's why we can just compare mx and the atomic mass of the parent and the atomic mass of the daughter. It turns out that there's another possible beta decay process, and it's sort of lumped in the same category, that involves a proton being turned into a neutron. So this kind of proton decay involves proton going to neutron plus a positron. This still counts as a beta process and a neutrino. Notice so a positron, by the way, is the antiparticle of the electron. It has the same mass but opposite charge. Again, notice that charge is conserved, so we have a plus charge here and a +1 charge on the right side. Also, lepton number is conserved since the positron counts as an antiparticle, -1, and then the neutrino counts as +1. And so, writing out this reaction in full, we get something like parent going to daughter. Once again, the mass number stays constant, but now the atomic number goes down by 1 since we're converting a proton to a neutron, and then we get our positron and our neutrino out. So once again, this can so this requires something to be true about the atomic masses. So it requires the atomic mass of X to be greater than or equal to the atomic mass of Y plus twice the mass of an electron. Okay, and so this takes a little explaining. So in this, so once again, like the neutron decay we had talked about earlier, this process, right, does not involve any of the electrons that were initially outside the nucleus in our parent atom X. So if I now, if I undergo this decay process and I decrease my atomic number by 1, right, I still have the same number of electrons outside the nucleus. So now my daughter atom Y actually has an extra electron compared to its normal state. And so we have to account for that when we're looking at the mass of the all the components over here. Right, we have the daughter atom, but what we actually get has an extra electron, so that's 1 Me, and we also have to account for the mass of the positron, but that is exactly the electron mass. Hence, this is the criterion for the initial stuff to have more rest energy than the final stuff. There's one other thing that is also considered a beta process, and it's something called electron capture. Unlike the other two, this one involves one of the electrons that is outside the nucleus within the atom. So it involves a proton and an electron combining to become a neutron, and whoops, I forgot my neutrino here, which I need to have to conserve lepton number. So let me just note that this is one of the atom's own electrons that gets captured, quite literally, hence the name. So you can try to guess how the whole process goes. I'll just still write it out. So we have our electron plus our parent here, A, Z, X. So that now becomes, so we keep the mass number the same, but we decrease the atomic number plus my neutrino. So again, notice that we're conserving both charge and so zero charge here, as well as lepton number 1 and 1 on either side of this process. Oh, and one more thing, the criterion for this to happen is this requires that the atomic mass of the parent be greater than the atomic mass of the daughter. Just to be clear on why, since this electron is already part of, comes from with this atom, the atomic mass of the parent already includes that. And then we lose an electron here overall, but because the atomic number has gone down by 1, an atom of the daughter Y has the right number of electrons. There are no extra or missing ones to account for, and so we can just look at its atomic mass here. One other kind of nuclear decay I want to mention really briefly is gamma decay. So a gamma particle is none other than a high-energy photon. We've been using the Greek gamma for photons all semester, and that's partly why this is called gamma decay. So just to understand this doesn't involve the nucleus changing. So it's like it doesn't involve a change in the atomic number. Rather, it turns out that nucleons in the nucleus experience a potential energy that's finite well-like. A finite potential energy. Energy. And as you know from studying the finite well earlier in 1D quantum mechanics, right, that a finite well has discrete energy eigenvalues, right? And so a gamma photon is emitted when there's a so the photon is associated with a nucleon going from some excited state to a lower energy state. So from excited to lower energy